We've looked at this graph before. Now we're going to take a step further though and ask not what is the slope at any given point, but we're going to ask what is the slope at all of these points and what happens when we graph it. So here we have the function f of x, and I claim down here we have the function f prime of x, which is equal to the slope values on the original graph. So this can be a bit head-bending at first, but let's work through it step by step. Let's take a look at the points a through b. We said the function was increasing along here, so where the function is increasing, f of x is increasing. On those intervals, we will see that translated to, well, we said that before, f prime of x being positive. And so what we should see here is positive values on this graph. Perhaps the most distinctive feature, though, is the zero value. If we take a horizontal tangent line, we can see that it occurs at B. We can see it also occurs at D and at F. All of those have slope 0. That translates to, well, f prime of x equals 0 or a 0 value on this derivative graph. And we can see that translation here and here and here. We get those values at those three locations being 0, or asking the question on this graph, hey, what's the slope of the original graph? When I hit B, the slope is 0. When I hit D, the slope is 0. When I hit F, the slope is 0. Last but not least, we can do the complement. When this graph is decreasing, or f of x is decreasing, what we expect to see is that f prime of x is less than 0, it's negative, and so we expect to see negative values on this graph. So positive values for this scenario for where f of x is increasing, and negative values here. That's exactly what we see, say on this interval to here. Between b and d, the function is decreasing, so the slopes, and these are slope values, are all below the axis. Take a moment to look at those two graphs, look at the zero slopes, look at the shapes. Try not to read too much into the relationship of the bumps. To me, these anchor points, or these definitions over here about whether the function is increasing, decreasing, or hits a zero slope point, those really define how you sketch this function down here, the derivative graph, because we can translate each of those properties into something concrete in the derivative graph, or the values of the slopes. The last thing I would add is there's a steepness relationship, that if we have steeper slopes, positive or negative, then that becomes more extreme values. And we see that in the relationship again on this steep decreasing point. Here's 0. The value of the slope is large and negative. Here the slope's not that extreme. We see positive values but not as extreme. Same thing for G. We see negative slopes but not as extreme as at C. So we get negative values but not as extreme as at C when we talk about the derivative graph. Now let's consider another example with this graph defined here. And again, look at the slopes that you can detect on this graph and whether they're positive or negative. And then we're going to look at 4 options for the derivative of that. Here's the original graph again. Here are the 4 candidates for the differential or the derivative of this graph here. Take a moment to consider each one of them, pause if you need to, and then we'll go through an analysis for detecting which one of these is the derivative of this graph here. So f of x and f prime of x, take a look. Coming back in, what do we notice right off the bat? We look for 0 points, points of 0 slope, because those translate, and it happens at 0. So we'd have to have 0 value at x equals 0. Right away, that rules out this graph here. This graph here would be saying f of x has slope 2 at x equals 0. And that's not what we see here. Our graph has slope 0. What else can we tell? Well, on this interval here, the function is decreasing, and so we have negative slopes. And so when we look at the derivative graph, we should have negative values. Let's call that here negative values, negative values. And here we should have negative values, but we don't see them. We see positive values, values above the axis, and so that rules out this possibility. Last but not least, if we look at what happens after x equals 0, we see the function is increasing. And I should be more specific with all of these, that f of x is increasing, so f prime of x needs to be positive, or we have positive slopes on the original graph. And the key thing is the positive part. Slopes are what we see on these graphs here because we're talking about the derivative graph. The positive is what we're looking for. And so we expect to see on these two intervals here, one of them should have positive values. And only one of them does. So we can X out this one here. So C is the only graph who, if you look at the value of the function here, a little bit larger than 1, a little bit less than 1, we see a slope that's a little bit less than 1 on this graph. When we get to around here, we see a slope of -1. Then we take a step to here, we see, yeah, it's pretty reasonable. We'd have a slope of -1. Negative slopes, 0 slope. Positive slopes, negative values, 0 value, positive values. We can also see that towards the end of the interval, may not be exactly 0 slope, but it's pretty close. And we see that translated into something close to a 0 value at the end of this graph. That's an extra confirmation that we were on the right track.